everyone. So I'm taking over the microphone, and we are going to start the first scientific session of this conference. And I'm very glad to kindly ask to take the Ursula Keller the stage. And she is from Federal Institute of Technology in Zurich, Switzerland, right? And very soon we will see from the topic that basically some of the talk will revolve around the frequency comb revolution. Now I'm wondering whether it has anything to do with another event which took more than like 50 years ago. Maybe some of you know, maybe don't. It's sometimes called quartz revolution. Yeah? And that actually reshaped the watchmaking industry in a significant way, especially so in Switzerland, because some manufacturers continued making the clocks with the mechanical movement, right? Which are not very precise actually, but can be very expensive. Some opted to make clocks with the quartz movement, right? Which are more precise, yet cheaper. And some, I think, took some time for thinking and then decided to work on some completely different type of clocks, maybe optical clocks, let's say, who are much more precise. And I wonder if we are going to hear about this today. So please take the stage, and we are going to have this.
Thanks a lot. So the microphone is working. Do you? Oh, yeah, it's working. Okay, great. Thank you very much. This is actually the second time I'm here at Open Readings, and we just tried to figure out before, it was 8 years ago when I've been here the last time. And let me start with, during the COVID, I finished a textbook. And this textbook is based on 30 years at university. And I tell, I'm towards the end of my career. I'm facing mandatory retirement, which is kind of a sad story. But anyway, we will have more of that during the panel. But when you're a professor, you have to teach your students very fast so that they can be productive. And the way I did it is everything we learned, I put into a lecture, and the lecture grew over the years. So this is a book which grew over 30 years, and then my students, who are now professors as well, told me I should really finish up these lecture notes into a decent book, which I did during COVID, because then you had time, right? It has about 800 references going back to the 1960s, and it starts with the Maxwell equation, and all the other equations are derived step by step, because, every single student hates these papers where you say, and then it follows, and then you have no clue how it follows. So this book is a promise. The follows is done in every step. I mean, I had even students telling me, there might be a step too much. Then I said, oh, well, if you're good, you can skip over it. But this is step by step. So I hope I'll leave this in the library. And I hope you find it useful, because I think once you know the basics, you can actually make the next step. And that's what I saw in my group. By the end, I will have 101 Ph.D. students graduated, and they were all extremely efficient. And without their help, I never would have done what I've done at the end. So let me start with two revolutions over a similar time frame of two communities which hardly ever interacted. One is this frequency metrology revolution. The frequency metrology revolution is then also defined the second, and it's the basic principle, as was already said in the introduction. You define the second by number of oscillation of a periodic signal, So a mechanical one or a pendulum is 1 per second, and normally one period of this periodic movement is the accuracy of the clock. So the higher the frequency, going from mechanical to quartz, which was mentioned before, the clock becomes more accurate. So the microwave clock was the standard, the best one for a long, long time. That was in the 9 gigahertz regime. You could count this electronically, each oscillation. And the optical clock came in as a new technology, and initially was pretty cumbersome to do because, you know, how can you count hundreds of terahertz? You can't. So you need to frequency divide it down until you can basically count it. And initially it was done very complicated. Today, with the frequency calm revolution, which is going over then to the modelocked laser, we reach an accuracy, fractional frequency uncertainty of 10 to minus 18, which is just amazing because this corresponds to an accuracy of moving a clock by 1 centimeter in the gravitational field, the change in time due to the general relativity theory. So if not Einstein would have proposed this in an earlier time, we would have measured it by now and discovered that something is happening and ultimately also discovered the general relativity theory. So this is an amazing accuracy that we have. And it has a lot of application because actually frequency is the most accurate observable that we have in physics. So if you can reduce something to a frequency measurement, then you can make it extremely accurate. So you can basically define SI units. I mean, the second can be now defined more accurately. You can look at probing for the gravitational details on the Earth as a sensor. There is some hope for gravitational wave detection, test of general relativity. Maybe there is more behind that. You know, if you can measure more and more accurately, maybe there is something else coming up. And of course, there is also the hope, maybe, that we finally can measure if the natural constants are actually constant. And that would be a new boost in physics, you know, which, because we don't really have a theory for it. This is all going to be big physics because, you know, as I showed you, I mean, 1 centimeter of moving a watch is already changing the measurement, and even a cloud going over your lab is changing the measurement, so you ultimately have to go out in space to do some of these measurements, and that is what is being prepared today. So all of this became possible with these optical frequency columns, and that's where, you know, the frequency metrology is suddenly connecting to the modelocked lasers. Frequency metrology normally wants to have frequency as narrow and as accurate as possible. And in the femtosecond, we want to have it as broad as possible. So how did this connect at the end? So on a similar time scale, this is the femtosecond revolution. You know, it also was a change in technology. In the frequency metrology, it was from the microwave to the optical clock, and here it goes from the dye lasers to the solid-state lasers. The dye lasers were the first lasers that produced the femtosecond pulses, and a lot of the basics were actually developed during this time, like dispersion, compensation, and so on. And there was a long-standing world record of 6 femtosecond pulses here by Shank at Bell Labs, but it was external amplification and pulse compression, and the pulses were really noisy. Okay, this all changed with the Ti-sapphire laser. This was really a breakthrough and a change in the game, because suddenly we had a much more reliable laser that could support the few cycle pulses directly out of the modelocked laser without any external pulse compression, with much more average output power. And this is something that we could do with these solid-state lasers. We had low noise, few cycle pulses, and that opened up a whole bunch of new application that I will briefly talk about. So these were the two revolutions of two fields which pretty much happened independently to each other until we met, because we had a new problem with these few cycle pulses. So when you looked at the few cycle pulses which came directly out of the modelocked lasers, we realized that the modelocking is only stabilizing the pulse envelope and not the electric field underneath. And once you have a few cycles underneath the pulse envelope, here, this fast oscillating thingy here. Oh, let's get the pointer going. Control L, I think. Let's see if this works. Ah, yeah. So now, here, this fast oscillating electric field underneath the pulse envelope. So from pulse to pulse, this was basically fluctuating. So this was a new problem. We had actually a Gordon conference where this problem, how to measure the position of the electric field underneath the pulse envelope and how to stabilize it, was considered a holy grail. Actually, to stabilize it was probably not so hard. The key question was really to get an error signal on the position of this electric field. Because we all knew that the pulse envelope propagates with the group velocity and the electric field with the phase velocity. So the control ultimately has to be with controlling the difference between the group and the phase velocity. Okay, this was 1995, the Holy Grail. And that problem we basically solved together with Telle, because we realized, and this is ultimately one line in math, okay, this is the amazing thing, is that this carrier envelope offset phase, as we called it, because the electric field is the carrier, the envelope is given by the pulse envelope, and that's the offset. So this CO offset phase, if you take a time derivative, you end up with a frequency. And the question is, what frequency is it? And you can show that with one line of math, that this frequency is the offset frequency of the modelocked frequency comb. Okay. So this, so when you look at modelocked laser with a frequency comb, then you have this equally spaced frequency of a pulse train, which is given by the pulse repetition rate. And then you have an additional degree of freedom, and that's the offset, and which then determines the position of the electric field. And then the question is, how do you get access to this offset? How do you get this as an error signal? Because once you have an error signal, you can stabilize it. It's kind of like, you know, in movie theaters, you know, Arnold Schwarzenegger, when he bleeds, you can kill it, you know. So it's pretty clear in physics. Once you have an error signal, you can stabilize it. Because then you just start moving things around and you find a way to stabilize it. So this is basically how these whole modelocked lasers entered the new regime, where we realized in this few cycle regime that we had two degrees of freedom. One is the spacing. And actually, I was fully aware of this physics because I did my PhD with Dave Bloom, who was the first to actually stabilize the spacing of these modelocked lasers to a microwave standards. So I was fully aware of the physics and the noise and so on, which then helped me to address these problems with the frequency offset here. Okay, and we learned how to stabilize this, but I don't want to really take more time to explain that all to you, because that's in the book. You can read it in the book. Because the laser evolved. And many applications with these frequency combs actually then ultimately required 2 frequency combs. And so you had to stabilize it. And then we came up with a new laser concept that actually removed all stabilization altogether. So this is always interesting because the stabilization ultimately gets you going to think along new ways. And then you get rid of the whole thing by realizing, oh, you can do it easier. I mean, this is something I've been watching over the years so many times, that actually you could have done certain things a long time ago, but you'd never started thinking along those lines, and that prevented you from making that invention. Even though you could have done it way before without the stabilization. So the frequency comb became a whole field on its own in frequency metrology, because you had with a stabilized frequency comb where you had the repetition rate and the offset stabilized. You had basically a ruler in the frequency domain, and you use this ruler then of the stabilized frequency comb to measure an unknown optical frequency. Because as I mentioned at the beginning, the definition of time depends on counting the oscillation, but you cannot count hundreds of terahertz. And so you have to divide it down. And the easy way to do that is by beating an unknown optical frequency on this stabilized frequency comb, and then you measure the beat signal. The beat signal is at less than half of the repetition rate of this mode-locked laser, and that one is typically in the 100 megahertz to 10 gigahertz, and this you can count. And that's how you got the 18-digit of accuracy in the optical clock. And that just tells you this is not the end, right? Because if we get a frequency comb with the high harmonics, with the same fidelity and stability, we can get seconds even more accurately, right? So, you know, we're not at the end at this point. And so far, which is also interesting, time has been always continuous, right? It has been a parameter. So it's, I think, you know, very interesting field, but the experiments will become very difficult because we're going to have to move up to space to not being perturbed, right? But that might not be such a problem. Okay, so this is basically where there was a Nobel Prize in laser-based precision spectroscopy, which is covering the work from microwave to optical combs, which then resulted in this new definition of the seconds with all the potential of application. But if you're really looking at the frequency comb alone, then I think you should make sure that you reference all 3 of this paper, which is this joint effort from the ultrafast community and the frequency comb revolution. So as I said, there was a lot of interest in dual comb, and that goes actually back to microwave. I mean, microwaves had frequency combs for a long, long time, goes back to the radar and everything. Many measurement concepts go back to the microwave, but this now we get suddenly these combs in the optical domain, and that has a lot of application. When you actually take 2 combs with different repetition rates, slightly different repetition rate, and I'll explain to you afterwards why this is interesting. But if you do that, you're going to have to stabilize both the repetition rate of these 2 oscillators and the offset. And the offset stabilization, I haven't really explained it, is a little bit more complicated to do. It is also takes more effort in terms of the stabilization. It's much easier to just do the repetition rate. And so at the end, this is a pretty complicated system, you know, which has this laser, but there is a whole rack of electronics to ultimately do the stabilization. You can buy this very expensively. But, you know, what we actually came up with is that you can produce 2 combs with 2 different pulse repetition rate out of 1 single laser. Okay? And then you say, gee, how does this work? because the pulse repetition rate is given by the round trip time of a pulse in a modelocked laser. And we all know in a modelocked laser, it's the cavity round trip time. So why do you get suddenly 2 modelocked pulses out of one cavity, out of the same laser cavity? How do you do that? Actually, at the end, it turned out to be extremely simple. The idea came actually with dual frequency. Some people use that to produce 2 frequency. Because, you know, when you add a birefringent crystal inside the laser cavity, and you share all the other parts of the laser cavity, then you can have 2 polarizations running in the same cavity. And because one beam is in this birefringent crystal, the ordinary, and the other one is the extraordinary beam, they have different refractive index, and because they have different pulse cavity lengths. And with this, just adding a birefringent crystal, you get 2 modelocked pulse trains out of the same laser. The other idea then came later on, which was spatial multiplexing. So you actually use a biprism, which is close to a flat mirror, but a little bit off, maybe by 1-2 degrees, so that the path through the laser cavity doesn't leave the laser cavity, but it's having a little bit of a different cavity length. And there are different pros and cons for these different techniques, but they're both very simple because you just add one simple passive element in your laser cavity, and out you get 2 modelocked lasers. So the question is then, how stable are these lasers? Do we need to stabilize it still, or can we do then these dual-com measurements without stabilization, which would be really cool for industrial application? So this whole dual-com application and single laser with dual-com generation has become a total hot topic. And during the COVID phase, there were a whole bunch of review articles. Some people wrote a book, some people wrote review articles. So there were a whole bunch of review articles. I'm mentioning this one because these 2 ones, because they give a really nice overview of the different applications that people can come up with these dual-com laser sources. I think everybody can get a copy of this view graph, so I think that's, that's a given. So what the question is then, if you produce this out of the same laser, how stable is it? Do you really need no stabilization to do these dual-com measurements? Okay. And this is basically then a new type of a laser, because why should we ever buy a normal modelocked laser if you can get 2 pulsed 2 coms out of 1 laser, right? You can always switch off one. So why should you ever buy a single com modelocked laser again? So, and I will hopefully get you excited and start thinking about dual com, because when you do any kind of measurement, you should think dual com, okay? Because that will make your life easier. And of course, you know, my group has a strong tradition in starting companies. And we also started a company because we really believe that this is something good. And Justinas is the CEO. It's a former PhD student in my group. So you can actually buy these lasers now if you're interested in these applications. So let me explain to you in 2 ways how this application works. Once you understood it, you can then start thinking dual com. And the whole thing is either based on thinking in the frequency domain or thinking in the time domain. And I want to show you how this is connecting so that, that you understand how this is working. So first, I will start with the frequency domain because that is how originally the frequency metrology people were interested in this dual-com application. So it is about possible application in spectroscopy. And the traditional, higher resolution spectroscopy is done with conventional Fourier transform spectroscopy in this interferometer. and you have basically one arm you delay, and you get this interferogram on the photodetector, right? If you come in with certain broad spectrum, short pulses, and you delay one arm, you measure then on the photodetector in, as a function of displacement, this interferogram. And if you then take Fourier transform out of this, you end up with the frequency, with the spectrum of the laser source that got into this interferogram, into this interferometer. So if you put in an absorber into one arm, then the interferogram will have this absorption in this interferogram as a function of displacement. And if you then make the Fourier transform, you see the absorption lines. And the larger the delay, the more accurate is the measurement, okay? And that also tells you what the problem is with this measurement, because it takes a long time, because you have to mechanically move this delay over a long distance to get the higher resolution. So with dual COM, you get that for free. So in the dual COM, you have basically these two COMs with different pulse repetition rate. And the pulse train, when at the initial time, the two pulses overlap, at the other time, they will be shifted, and they will shift it more and more. And so if you send this onto a photodetector, they will overlap to each other over time, and then also create this interferogram, very similar to this interferometer, but instead of displacement, it is time as these two pulses move over each other. And this interferogram repeat at every 1 over the difference in the pulse repetition rate, okay? So at the end, the whole measurement then only takes 1 over the delta f rep. So assuming the delta f rep is 4 megahertz, one measurement of this interferogram is only taking 0.25 microseconds. Okay, so it's a very fast measurement. And so just to be clear now about the terminology, because which I use all the time, and I see that people sometimes mix this up. So normally when you talk about these modelocked lasers, you think about the optical COM, which have here the 2 repetition rate. If you look at the time domain, you have the 2 pulse trains with different repetition rate. If you then put these pulses onto a photodetector, you end up with these interferograms, which are repeated at 1 over delta f rep. If you Fourier transform this, you end up with the so-called microwave COM. So when so they're all connected, but I talked then a lot of the key is, the simplicity is that you push all the measurements into the electronic domain, into the interferograms, into the microwave COM, because then everything becomes very simple, fast, and it's basically a scope, an electronic measurement instead of an optical measurement, okay? So with this spectrometer, you send basically these 2 COMs through this gas cell, and when you look at it in the optical domain, you see these 2 COMs, and the microwave COM is then the beat signal of all these COM ticks at different repetition rate, which then gives you this microwave COM, and the absorption here is translated into the absorption at the microwave domain, okay? So this measurement of this absorption then is very quick, because you don't need any mechanical parts. But traditionally you need 2 frequency COMs, which requires 2 lasers. And this is what we addressed with these single cavity dual COM lasers, because as I will show you then later on, once I explain to you a little bit about the noise of these lasers, understanding the noise of these lasers, that actually for the measurements you don't need any stabilization anymore, because it's fast. Fast measurements means it's less sensitive to noise. Okay, So we did this the first time with a free-running dual-comb laser. After we demonstrated it, we then did a measurement. The first laser was done in the near infrared at 1 micron, and then we kind of looked around. We are not spectroscopy expert. What can we measure in absorption? Water has a little bit of absorption even at 1 micron. And we then measured the water absorption with this dual-comb laser. And you measure it basically in the time domain on the photodetector with the interferograms. The interferograms have all the information. You Fourier transform these interferograms, and then you see the absorption line in the microwave spectrum, which you can then translate into the optical spectrum. And we could convince the science editor that this is really a paradigm shift in terms of the dual-comb measurements. And we got it published in Science, which was nice. And then we kept going. And for example, we also used it. So we also used it, for example, for the terahertz time domain spectroscopy. So where we used one comb as the pump to produce a terahertz pulse that is propagating in air again, measuring water absorption in air again, but now in the terahertz domain, and then using the other pulse, which is at a different pulse repetition rate, to do the probe and do the detection here, which then again produces this interferogram. And you can actually integrate this over 2 seconds, because without any stabilization on the laser, as I will show you later. And then when you take the Fourier transform of these interferograms, you get then the absorption line of the water in the terahertz spectroscopy. And the key is that, you know, you have it over a long spectral window. Actually, you see here something. We wanted not to get close to this one because this was actually a reflection from the detector going back to the emitter and coming back. So that would have disturbed the absorption measurement, so we stayed away from this one. So this was the window that we used, 500 picosecond delay line. This would be in a mechanical, which is of course mechanically very difficult, but optically dual-comb, no mechanical delay line. Alignment, no problem. And basically we got up to 55 dB of dynamic range in 2 seconds integration time. And the whole terahertz spectroscopy becomes a scope measurement. You know, so this is basically a real lab measurement where we then add a sapphire substrate into the terahertz beam to then measure, for example, the refractive index of the sapphire crystal, or if you know the thickness, you can, I mean, you can either measure the thickness or the group refractive index, because you do it with pulses. And, you know, this is live measurements in the lab. You know, the absorption in it, and then you put in the sapphire crystal, and then you see the absorption, you know. And this is with a mechanical delay line traditionally of 500 picosecond, and now you see it measured like this, right? And that's the power of dual-comb. You can reduce any pump probe measurement to that kind of things, and that's extremely, extremely good. Let me explain how to think it in the time domain, you know, because everything you can understand in one or the other, and normally one application is easier in the frequency domain and one is easier in the time domain, but in principle you can explain it in both domains if you really understand things. Doubly, people know exactly what I'm talking about, right? So, in the time domain, you have 2 pulse trains with different pulse repetition rate. I want to explain equivalent time sampling. This is what my professor did when I did my PhD, okay? he stabilized a modelocked laser to a microwave synthesizer and used it for electro-optic sampling. And it just tells you things are coming back. You know, once what you learn in your PhD, you can always use again. And later, and the funny thing is, you know, my professor was a double E, and so he called this technique equivalent time sampling for reasons which I'm going to explain to you, because it's actually well known from the microwave. At the similar time, there were some physicists for spectroscopy, and they did something similar with dye lasers, which you could tune in zinc pump dye lasers, where you could tune the pulse repetition rate with one single pump to a little bit different pulse repetition rate, which was pretty stable. But it was here, for this application, only the pulse envelope. Okay, so it's a pump probe experiment where you only care about pump and probe the pulse envelope, for example. So with this pump probe experiment, you measure, for example, a nonlinear mirror or a SESAM, you know, where the reflectivity goes up because the pump is bleaching the absorption, and then the absorption is recovering at a longer time scale. So you go and induce this with the pump on a periodic measurement, and then you come with the probe at a different repetition rate, and because it's a different repetition rate, the probe will hit the sample always a little bit at a different time to then sample the response of this pump probe measurement, right? So you make this fast measurement, which normally is in the pico-femtosecond domain. Here, you know, the pulse repetition rate was 137 megahertz, so the pulses repeat at 7.3 nanosecond. The recovery time is maybe hundreds of picosecond or picosecond, and you translate this measurement into an equivalent time window of 1 over delta f rep, right? Because that's what it takes to repeat the measurement. So you translate your nanoseconds into microsecond, that's the equivalent time. And you then can see this pump probe signal on a scope without a mechanical delay line, right? And that's why it's called equivalent time sampling, an idea which goes back to the microwave domain. And this shows you, for example, the measurement on a scope, where we use here a trigger signal when the two pulses overlap. For example, you go through a nonlinear crystal and do some frequency generation or whatever, and then get the trigger signal, right? And then below you see the response of this nonlinear mirror as you increase the pump power. And you can just measure it, you know, on a scope. The whole pump probe measurement becomes a scope measurement, becomes an electronic measurement. And as soon as it's an electronic measurement, it's simple, right? So you can do it also with pump probe in the picosecond ultrasonics. So picosecond ultrasonics is an old application, is being used here. I mean, the principle is very easy. You come with a femtosecond pump pulse, you produce a perturbation at the surface here, and you create, you know, for example, heat absorption. You create a mechanical shock wave that is propagating then inside these samples, and an acoustic wave at every instant where you have an impedance change, you have a reflection, right? A partial reflection. And this partial reflection ultimately comes to the surface again and modifies the surface, which you can then probe with another probe pulse delayed as a function of time, right? So it's, again, a classical pump probe experiment. But the advantage of doing that with acoustics wave instead of light is that you can go through opaque material. So, I mean, you need, for example, the speed of sound is much slower, so it's 5 nanometer per picosecond. So with 100 femtosecond pulses, you can get already 2.5 angstrom resolution. And, you know, with a 10 nanosecond scan rate, range, and so 100 megahertz laser repetition rate, you can scan over 25 micrometers of structure. So assume you have a multi-layer coating, metal and whatever, where normally you can never get an optical signal through. You can then do this measurement. And for this you need really high accuracy because the small little perturbation of all these partial reflections are small. So you need a signal to noise of 10 to minus 5, 10 to minus 6. And this is, for example, a measurement that we did also on a sample, on a simpler sample, where you see this reflection measured with the pump probe with such a dual column laser. Again, it becomes an electronic measurement on a scope, right? All pump probe is reduced to electronic measurements. So I hope I got you really excited about this. Now I want to explain, to you about noise. So noise is really something that matters, okay? And this is another spin-off company out of my group. This is a technology that got used in 3 startup companies. So the one, getting short pulses at 1.5 micrometer at high repetition rate was, of course, interesting during the whole telecom bubble. And we started a company, which, of course, went up. Gigaterra was the name of the company, which went up and then down. There are like many of those stories during the telecom bubble. In between, I thought I'm never going to have to write a proposal. And then everything disappeared again, and so you go back and do your normal job, And this is basically a diode-pumped SESAM modelocked erbium-ytterbium glass laser, which is extremely low noise, and this is the lowest frequency COM that you can get at these wavelengths commercially available. It's being very successful, and NIST and Max Planck and all these people are buying this laser now. This is not something that was clear at the beginning, that these lasers will actually be low noise, because there was a very famous paper, and this got lost a little bit because the author was Herman Haus. And, I don't know why that happened. But anyway, so it's a paper from 1976, which actually said that it is not possible to passively modelock solid-state lasers like neodymium because of Q-switching instabilities. It's always great when famous people tell in a paper that it's impossible, because then you can come and do the impossible thing. And that's what I was luckily doing. Not that I didn't believe this expert. It came only later on that I stumbled into this solution. But anyway, there it was. It was this paper. It said in there, stable passive modelocking is unachievable for solid-state laser. Steady-state modelocking is prevented by a relaxation oscillation. Great, right? And that was the beginning of my career, because I showed it with the SESAM that this is possible. And why was this famous guy predicting this? This is the problem of numerics. You only get what you put in, right? So he did a lot of the numerical experiments and varied the parameters in a range which made physical sense, and that was a certain type of material he had in mind. And with the inventions of of Ti-sapphire lasers, and then ultimately using other solid-state lasers and using the semiconductor saturable absorber, changed the parameters in a totally different regime, which he did not look at in his numerical experiments, which he explained all the prior attempts with dye saturable absorbers, but he didn't vary the parameters large enough, and then you don't get. And that's why we do experiments, right? We do things, and suddenly something works, and then you better know why, learn how it works, okay? So in modelocking, you have a gain, and you have a laser cavity, and then you have a loss modulation. And traditionally, all solid-state lasers were modelocked with active modelocking, so it's an acousto-optic modulator, a sinusoidal modulation that then gives you these pulses. Now, with the semiconductor, I could get a much stronger modulation, which opened up a net gain window, which was much shorter than with the active modelocking, getting shorter pulses on top of it. At the end, it was also more stable. So it basically, so this semiconductor was a passive mirror, which you designed this response into this material, and this replaced all of this one, and everything was working better, and it was cheaper. So that was the start of my career, and that was my know-how that is ultimately going into this one. And I invested a lot into designing these SESAMs, and that was my key know-how from which I build up all the rest to a certain extent. I always tell the students, you're good at something, and this something is your currency, how you then collaborate with other people. Because a lot of people wanted to collaborate with me because I had the SESAMs. And then I got a whole bunch of things going, and actually the dual com doesn't work so well with fibers, but it works perfectly with SESAMs, right? Because it's like a mirror, and it modelocks both beams, right? Once again, even 25 years later, this technology was a key technology. And this is something where I basically just used semiconductor materials where you design the nonlinear loss modulation, because it's very simple. This was all done in the 80s. The basics is that, for example, when you come with a short pulse laser, you take electrons out of the valence band, put it into the conduction band, and as you fill up all the states, the absorption gets bleached. And then these electrons thermalize. That gives you an initial fast interband thermalization. And then they recombine. And in a good semiconductor, this can be hundreds of picosecond to nanosecond, which would be too slow, because we need a faster saturable absorber for all the modelocking of the solid state. And so we introduced mid-gap traps with low temperature grown semiconductor. That's how I started it. There's a whole story behind it, why I got into it, because it was also solving another problem, and without me knowing even about the defect dynamics. It was actually interesting how sometimes it comes, but that would be a talk on its own. The nice thing is, this is mature technology, which has a huge market, optoelectronics in semiconductor. You can control everything in semiconductors. And that's how this became so successful. And because you can actually see nicely that you can solve the Q-switching instability, because you have the mode-locked pulse train in the microwave domain. So this is around the first harmonic. And normally you have this relaxation oscillation here, which are showing up as side peaks around your laser harmonics. And those you need to suppress as much as possible. If it's not suppressed, you go into Q-switch mode locking, or even worse, in just noise generation. So I had a way of solving this Q-switching problem. I knew how to measure the quality of the suppression of the Q-switching, because my professor was an electrical engineer, so I learned all the stuff from him. And with this, we basically got SESAM mode-locked solid-state lasers out there. And amazingly enough, the better you suppress these Q-switching instabilities, the better and less noisy these lasers are. And there is a good reason why erbium-ytterbium glass is the lowest noise, because it's an energy transfer between the ytterbium to erbium, and that gives a low-pass filter and suppresses the relaxation oscillation. But this is also in the book. So let me now explain you a little bit more about the laser physics, because, okay, I'm running out of time. So how did the lasers get up going? So the whole invention came with us working on these optically pumped semiconductor lasers. So that was a new type of laser where basically the gain was a semiconductor optically pumped. And because the SESAM is a semiconductor, we came up then with the invention of the mixel, where both the absorber and the gain was in the laser. And then if everything was adjusted right, you just pump this chip, this mixel chip, which had the gain and the absorber, in a simple linear cavity. And you got modelocked pulses out of it. So, you know, for a lot of application, you need gigahertz pulse repetition rate. So this is a cavity length of about 5 centimeters, right? So this is not something which you can do just on a chip. So there is an extended cavity. And the way we came up with this invention was that there was actually the so-called VCSEL, which is without the absorber in it. And people did, with birefringent crystal, did dual frequency lasers. And then we figured, oh, well, we can do this with dual mode locking. So by just adding a birefringent crystal into this linear cavity, pumping the mixel at 2 spots, works for both polarization, we got 2 modelocked pulsation. And that was used then ultimately for the SESAM. And that got us going to think about these things, right? We could have done this a long time ago, right? But you didn't think dual comb. And we didn't think along those lines. And then, of course, once you open the gate, right, you just put a lot of smart people on it, and then, you know, you just start cooking, right? I mean, so we did that also, for example, in diode-pumped solid-state laser. There's good reasons why you want to do it with also diode-pumped solid-state lasers. We did it here with ytterbium-doped lasers, and all the same cavity. And you design the SESAM correctly so that all the Q switching is not a problem, and you get these 2 modelocked pulse trains with very beautiful, nice soliton pulses, and the relative RMS timing jitter is extremely low. And the key is, if people talk about noise, you have to do it over what frequency span you're measuring it. So once you come up with this one, this is not such a big step, that you then come up with this spatially multiplexing, which is basically just replacing one of the flat mirrors with this one. And then they go a little bit different path lengths, and you get 2 modelocked pulse trains. They're not exactly the same because they hit the SESAM at 2 different spots, you know, so the homogeneity of the SESAM is then relevant. And you can tune it. The tuning of the different repetition rate, because sometimes, you know, you want to make a measurement fast or a little bit less fast, because it depends on your time resolution, on your scope. And you can change that on the fly without any mechanical delay lines. So the tuning of the delta F rep is important. And this is just a translation of the birefringent crystal, which then changes the different cavity lengths. And that gives you the tuning. And with this, we did another world record in terms of low noise. This dual comb, we had to come up with a new way of measuring noise, which actually applies to any dual comb sources. So this should become a standard, how we measure actually noise. And you can do it not only in reflection, you can go also in translation. On a gigahertz. This is, for example, a laser which we built with 3 watt in each comb, 78 femtosecond at 1 gigahertz, and you could tune the pulse repetition rate. And what is important to explain why it works, that you can do the measurement without any stabilization, is you make the measurement fast. So when you measure the noise, this is the timing jitter as a function of frequency. So this is the noise frequency. At what frequency this arrival time of the pulses are fluctuating. And this is a typical behavior of all the solid-state laser, that they roll off. This is on a log scale up. They roll off here with increased frequency and ultimately end up into the short noise. The question is, where are they ending up in the short noise? When you do a measurement, it takes a certain time. As you remember, the measurement takes 1 over the delta F rep. So that means, sorry. Here. That means that, something is missing here, so that's why. That means only the noise up above delta F rep is basically adding to the measurement. So the higher the delta F rep, the faster you make the measurement, the less noise you have. And so for most application, if you make the measurement fast enough, it's more than good enough. And also because it comes out of the same laser, the uncorrelated noise of the delta F rep is substantially reduced. So this is in a free laboratory laser, not packaged yet. So you have a lot of mechanical noise in the low frequency regime. And even that one gets suppressed because of the shared cavity of the two combs. So everything is actually very easy to understand. And, you know, there is always a trade-off where if different applications need different laser parameters. So when you do spectroscopy, if you make the measurement too fast, then the microwave comb starts to become overlapped with the neighboring microwave comb, because the spacing in the microwave comb is given by the delta F rep, so making it faster and faster, making delta F rep, making the measurement faster, measurement time shorter, delta F rep larger. It makes the microwave comb wider, and as soon as they start overlapping, you have aliasing. Then you cannot do the measurement anymore. So there is a sweet spot for each application, which you have to optimize for signal to noise and repetition rate. And basically, normally, you want to keep the delta F rep as high as possible. And that's why for many applications, a gigahertz pulse repetition rate is perfect, because it allows you to have a broader microwave comb. And now the other thing is, as long as you can measure electronically the slip of the RF comb, then you can actually track this interferogram and just make, every time this measurement is done, you make a shot of this interferogram and keep track of the movement of this interferogram, because this laser is free running. So if you do it for a long time, it of course will shift. But if this shift is small enough, you can track it and you can just average it. So when we average over 2 seconds, we just measure it, 1 over the delta F rep, keep the track and add them and do a frequency shifted interferograms, which is just a computer program. Everything is electronics, right? And then just averaging it over a longer time. And the key is, on all these lasers, is that basically the phase, this offset phase now on the interferogram, in the second derivative should be less than pi. And solid-state laser provide that. You're not going to get this out of every laser, this I can tell you. So even so, you know, this interferogram is fluctuating, right? But it's not too much fluctuation. So you see how the phase is drifting over 400 milliseconds of this laser. And then you can see the derivative, you can actually nicely, it's not random and incredible noise, you can track it on each of these drifts. And the second derivative is less than pi. And as long as you have that, you can then do the interferometric, you can measure these interferograms, shift them and add them and coherently average over a long time. And that's why you don't care about stabilization anymore. You just need a good enough laser. And, you know, we did that recently also with the Mixel at 2 micron, because with semiconductors, you can push it into the 2 micron regime, and we can do it too. So I hope with this, I could convince you. We've done now a whole bunch of applications. Once you understand it now, you understand, you can use it for everything. So we normally go out and work with experts in the field and collaborate and hopefully write some paper, and then hopefully from now on they will buy the laser. And so this is it. So during my career, people sometimes ask me, how did you end up doing all of the stuff that you end up doing? And it's sometimes scary for PhD student getting assistant professor and starting off. You're good at something. And that opens up collaboration, and that's the beginning of a journey, which is just an incredible journey, I have to say. I mean, after more than 30 years, this is a dream job, and they really have to beat me out of my job. I mean, I could go forever, and it was an incredible time. And a lot of things really happened by running into some problems. I always tell the students, if the experiment doesn't work the way you hope it works, that's the beginning. Might be just a dead cable, but you need to figure that one out pretty fast. And because they are very well educated, they know very quickly what the problem is. And and every time we solved another problem, we entered another field, right? Let me just guide you through it. So I started off with applied research, which is good for women, because then if you make a better laser, peer review is easier. I have more power and shorter pulses. That's it. Not the same in fundamental science. Oh, is this of significance, So for women, it is easier to start in applied research, and that's how I got my independent research position as a professor. And then I could do whatever I want, right? So I then went also into fundamental research, and at the beginning, I just pushed power, pulse duration, and shorter pulses. And every time we run, when you get to shorter pulses, somewhere it stops. And then you think, what happens when it stops? And that opened up, as I explained to you, it opened up frequency metrology to me. And that one made us, and then SESAM modelocking also got us into semiconductor lasers. And then because we were starting thinking about frequency combs, we then came up with dual comb modelocking, and that started another ERC advanced grant. The shorter pulses and the stabilization of the electric field ultimately got us into attosecond science, which also got me the invention of the attoclock technique, which then also got me an ERC grant. And that was a whole section of my research, which I haven't really talked about. But it always was, when I went into attosecond science, I didn't know anything about attosecond science. So I looked around, who are the people in the field who know about it? And I went to Anne Lullier and did my sabbatical with her. I just visited her and said, can I come to you? And so I did a sabbatical with her, which was a real pleasure. And that got me into attosecond science. So I would not be worried at the beginning. Just get yourself an independent position and start the journey. And you're good at something. And with that, you're gonna be, for sure, safe and have a fun life. Okay, with this, I want to conclude. Thank you very much. I was a little bit longer. So.
Yeah, okay, thank you very much for the interesting talk and very enthusiastic. So we're going to have some time for questions, I believe, and we have a separate microphone, so please raise your hand. We can give you the microphone and...
Like this? Okay, yes. Nice, thanks. So thanks for the wonderful talk. I was just wondering, so for SESAMs, so of course a lot of that is knowledge of how the lasers work, but also a very big part is the semiconductors. So how much of that did you do in-house, and did you use some commercial suppliers for the semiconductor things? How did that part go?
Yeah, that's also a good story. So initially I started at Bell Labs, and then of course I had access to the semiconductor there. And I realized when I then became a professor that I need to invest into my core technology that I need to do my work. So I invested a big part of my startup funds into the semiconductor work. So initially, So I went to ETH and said, I need an MBE machine. And then they said, too expensive. And then they gave me access to the IBM MBE machine because that was in the 90s. That was a little bit of an industrial downturn. And so they were glad that I hired a postdoc and had access to an MBE machine. And so we basically did everything on our own because we couldn't buy the EPI because we needed to destroy the wonderful property of the long-lived electrons in the semiconductor by this defect engineering. And we couldn't buy that at that time from any commercial vendor. So we needed to build it up on our own. And I then ultimately teamed up with a whole bunch of new professors who all came to ETH and said, where is the clean room? And, you know, ETH for a long time had so much money that each professor had their own subcritical clean room. And then ultimately it became clear that you can't afford one. And so the next generation, the younger generation, all wanted to have a shared clean room. And so I teamed up with other professors, wrote a proposal, finally got the clean room at ETH, established the first lab. And that's where I finally got my MBE machine, which I had to share with other professors, but 50% was for my use. And that's, so I maintained that material know-how in my hands. And I invested a lot of money into it, but that was something I knew about really well, and other people had not access to it. And that was a competitive advantage. You know, at the end, you know, there's a lot of smart people. Once it makes click, you know, a lot of people jump onto it. But if you have a crucial technology that only you have for a while, that gives you a competitive advantage. And so I cleaned up, right? That's basically the ideal situation. Invest in some of what is really important. But that was also at Bell Labs, right? A lot of people did their careers. When you look at analyze, why did these people modulator, you know, all this stuff, these people just happened to be at the right place, at access to cool technology, and then were smart enough to do the right thing. But having crucial technology, you know, if fiber laser is your things, maybe, you know, having producing your own fiber lasers makes a difference. Look at Philip Russell. So definitely invest into core technology as an experimentalist that you control. Yeah, exactly.
Okay, thank you. Maybe one more short question. Okay.
A lot of young people, so I just want to ask you a little bit to dream about the period of 10, 20 years. In which direction all the femtosecond science could develop? What is your thinking? What you are telling to your students? Just
you know, to be honest, when I started, I never ever dreamed of getting into the frequency metrology, getting into the attosecond science. I mean, this came totally unpredictable. So my key advice to the young people is keep a broader perspective. You go to the conference for a good reason and look around you where you can use your know-how to go into something else. So that when something happens, you know, in hindsight, everything is clear. But when it happens, it's the same when you start a company. In hindsight, everybody says, oh, you had it easy. But, you know, when it happened, it wasn't easy, right? So it's the same thing. You know, when it happened, you know, I just felt like, you know, for example, how did I get into the attosecond? It was clear that that basically the shorter and shorter pulses, it was an end on the femtosecond, how to get shorter. And so you had to increase the frequency. And there were the emerging things. So when I did the sabbatical 2001, there were already the first pulse. During the sabbatical, it actually happened with Anne Lullier. She did the high harmonics. When the high harmonics were there, people were already saying, hey, there might be attoseconds in there, but it wasn't so clear. It was actually, you needed to understand also the physics, the phase matching. That was Anne Lullier's path to fame, right? She just shot with a strong laser into a gas and discovered the plateau. And then she said, oh, plateau, this is not normal nonlinear optics, because nonlinear optics rolls off. She was clever enough to try to understand it, right? And that was her path to the Nobel Prize. And then during this time, the time I did the sabbatical, 2001, I believe, September 11 was also then, the first attosecond pulse train happened, and the first attosecond pulses happened, right? That is a new field. So do you want to go into this? Might be not a bad idea, right? Or a new material coming up. So predicting the future, I mean, I would say it's, I'm as bad as anybody else, predicting the future. And actually the real breakthroughs are not predictable. So just keep your eyes open and get a good basic education so that you're good at something, which you then can apply when things happen. Because when things happen, you need to act fast. You need to recognize it. There are people at the same time, they did not see it. And that's the difference, right? So keep your mind open. That's why you go to conferences, look around, always ask a little bit other people, what are you doing? Why is this cool? And then suddenly you make a synergy because you bring something which is unique. And as soon as, as long as you keep being interested and it's fun, and you're going to find something. But I think, we are not very good in predicting the paradigm change, right? As humans, we're good in linear expansion, but not in the breakthrough. Breakthroughs are normally unexpected and surprising. But when it happens, some of you see it earlier than others.